New images captured by the James Webb Space Telescope have left researchers both astonished and unsettled. Rather than deepening our understanding of the universe, these images have exposed a troubling reality. Our current theories may be insufficient to explain the origins of the cosmos. As our understanding of the universe's beginnings reaches its limits, we are now forced to consider new hypotheses about its formation. This discovery challenges even the most seasoned space experts, compelling us to reassess the Big Bang theory and delve into the intricate details of this groundbreaking revelation. To understand this discovery, we need to revisit the concept of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion within pre-existing space. Rather, it marked the beginning of space itself, along with matter and time, approximately 13.8 billion years ago. This event emerged from a unique phenomenon in physics and cosmology, known as a singularity, where gravity is so intense that the curvature of spacetime becomes infinite. Fast forward billions of years, and we observe that our universe is part of an ongoing, expansive relationship with space, expansion that is vital to understanding the universe's structure. Space itself continues to grow in size, rather than simply expanding into pre-existing space. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, signaling the end of the so-called Dark Age, when the universe was devoid of luminous objects. This era saw the formation of the first galaxies, though how quickly these galaxies developed remains an enigma. In July 2022, the James Webb Space Telescope delivered a key piece of information. Specialists reported that the telescope had detected several galaxies that already existed around 300 million years after the universe's creation. These galaxies, smaller and less massive than those that formed billions of years later, initially fit the accepted scientific model, which posits that the density of matter in the young universe was insufficient to form large galaxies. However, this discovery took a surprising turn. Rather than identifying smaller dwarf galaxies as expected, the James Webb Telescope revealed 6 incredibly luminous redshifted spots, early galaxies that were nearly as massive as the Milky Way. This startling discovery triggered one of the most significant cosmological crises in recent times. Despite their age being similar to previously recorded galaxies, these newly discovered galaxies were unexpectedly massive, raising a compelling mystery in the field of astronomy. After examining a series of images captured by the telescope's near-infrared camera, experts identified light sources that took over 1 billion years to reach Earth. This means we are observing galaxies that existed between 570 and 700 million years after the Big Bang. These early galaxies, however, were much larger than previously believed possible, contradicting nearly all conventional cosmological theories. Instead of dwarf galaxies, massive structures similar in scale to the Milky Way had already formed in this early epoch. One of these galaxies, in particular, was estimated to be over 10 billion times the mass of the Sun. If confirmed, such a discovery would present a profound puzzle, as it implies that there was far more matter in the early universe than previously thought. This discrepancy challenges nearly every standard cosmological model. To explain these structures, the density of matter in the early universe would have to be much greater than currently accepted. This discovery suggests that these galaxies may have formed through processes that are still completely unknown to us. The revelations made by the James Webb Space Telescope are prompting widespread discussion, with many researchers now questioning the validity of the Big Bang theory. A growing number of space experts, who have long held alternative views, are gaining attention in scientific journals. Even those who still defend the Big Bang theory are being confronted with fundamental questions that remain unanswered. Among these questions is the nature of the Big Bang itself. Did something emerge from nothing 13.8 billion years ago? Was there a triggering event, or was it purely accidental? Noted physicist Stephen Hawking argued that the concept of time as we know it began with the Big Bang, meaning the event could not have been triggered by something else. But even this leaves the mystery unresolved. Another puzzling aspect is the uniformity of radiation and matter density across the universe. No matter where or how far we look, the large-scale distribution of galaxies, nebulae, and radiation appears consistent. Some scientists explain this by invoking the theory of cosmic inflation, which suggests that the universe expanded rapidly in its early moments. Others have expanded this idea into the concept of chaotic inflation, which posits that inflation stopped only in certain regions, like bubbles, and continues indefinitely elsewhere. This theory raises the possibility of multiple universes, each with its own unique physical laws. In light of these new discoveries, we must also consider the radical possibility that the universe we observe is just a part of a larger cyclic structure. Some theorists suggest that the universe undergoes a cycle of collapse and rebirth, with a Big Bang being just one event in an infinite series of cosmic cycles. However, this is not the only alternative view. In 1955, a paper proposed that there may never have been a Big Bang at all. Instead, the universe might have existed eternally, with matter constantly forming and evolving in such a way that it gives the appearance of expansion. There are also more exotic theories to consider, some rooted in quantum physics and string theory. These ideas propose that our universe and everything within it could be a projection or simulation from a higher dimensional reality. While this may sound like science fiction, it aligns with concepts like the Kardashev scale, which measures a civilization's technological advancement based on its ability to harness energy. Exploring the depths of cosmology and the origins of the universe continues to be a journey of profound mystery. As researchers analyze these stunning images from the James Webb Space Telescope, the latest images captured by the James Webb Space Telescope have sparked how much there is yet to discover about the very fabric of our reality, challenging established theories and urging researchers to reassess fundamental aspects of cosmological understanding. At the heart of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, expanding rapidly and giving rise to space, time, and matter as we know them today. This monumental event was not just an explosion in pre-existing space but marked the very beginning of space itself. The concept of a singularity, where gravitational forces become so extreme that space-time curvature becomes infinite, underpins our understanding of this primordial moment. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structure formed in the early universe. These galaxies, identified within a few hundred million years of the Big Bang, appear surprisingly mature and massive compared to what current cosmological models predict. One of the critical questions raised by these findings is the nature of cosmic inflation. According to the dominant theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly. This expansion helps explain the uniformity of the cosmic microwave background radiation observed across the universe today. Yet, these recent discoveries suggest complexities in the early universe's development, potentially requiring adjustments to inflationary models. The rapid development of galaxies, as observed by the James Webb Telescope, compels cosmologists to reconsider the conditions and processes governing the early universe. These galaxies, now significantly large and massive so soon after the Big Bang, imply a density of matter that surpasses previous estimates. The mystery deepens when considering how such massive structures could form and grow in such a relatively short cosmic time. Furthermore, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain unclear. In parallel with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the conventional Big Bang view. Some theories propose that our universe is just one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advances in string theory and quantum cosmology, suggest a more complex and interconnected reality than previously imagined. One theory gaining traction is the concept of eternal inflation, where universes continually emerge from a larger, inflating space. This hypothesis posits that our universe could be just one bubble among countless others, each with its distinct properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the boundaries of empirical validation. Another provocative theory suggests that our universe may exist within a simulated reality, akin to a computer-generated simulation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable fidelity. If true, our perception of reality as a tangible, physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advancements in observational cosmology continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its extraordinary sensitivity and resolution, promise to uncover even more of the universe's mysteries. Future observations may shed light on the universe's earliest moments, offering clues about its ultimate fate and the underlying principles governing its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models such as quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be emergent or even illusory at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our comprehension of the universe's origins and evolution. As we stand on the brink of a new era in astronomy and cosmology, fueled by technological advancements and theoretical breakthroughs, we are reminded of the profound interconnectedness of all things, from the smallest subatomic particles to the vast cosmic structures spanning billions of light-years. The universe reveals its secrets to those willing to explore, and the exploration of the universe and its origins transcends disciplinary boundaries, challenging our fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and prompt new questions about its development and evolution. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic inflation, we move closer to a more complete understanding of the universe and our place within it. Through collaboration among astronomers, physicists, philosophers, and technologists, we embark on a grand quest to decode the cosmos, an endeavor that promises to redefine our understanding of existence itself. Whether exploring the depths of black holes, mapping the paths of distant galaxies, or contemplating the nature of reality, each discovery brings us closer to unraveling the intricate tapestry of the universe. As we venture further into the cosmos, guided by curiosity and driven by a desire to comprehend the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment embodies the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of both the universe and ourselves. Thus, the exploration of the universe is not merely a scientific pursuit but a profound human quest for knowledge and meaning, a journey that transcends the boundaries of space and time, inviting us to reflect on our place in the grand tapestry of existence.